Thanks very much for having me. So this is the paper right there that I posted at the end of October with my PhD student, Mohamed Meza, who is, I think, online. Um, so, as Marco said, the idea is to attach a moduli space to a quiver and a compact Lie group, where you have this Lax equation on the edges and a Kirchhoff law on the at the interior vertices. And the point is that, well, one of the idea is that if you think of the quiver and kind of inflate it to a surface, it turns out that up to symplectomorphisms, the moduli space only depends on the topological on the topology of the surface, and then we explain how they glue how these surfaces glue together to form some kind of functor, which you can interpret as a topological quantum field theory. And then yeah, so that's the idea. Let me just go over this more slowly. So is the sound okay?
Sound is okay, just very bass heavy. It's just your voice, I think.
Okay. I can try something else. Um, is that better?
It's the same, but we've made you louder, so there's no difficulty now. No, yeah.
Okay, I'll just continue like that. Okay, so this Lax equation. So this is an equation for pairs of maps from I an interval to a Lie algebra, which we'll take for this talk to be the Lie algebra of a compact Lie group. Although the Lax equation is more general, but so the Lax equation is an ordinary differential equation for these maps, which takes this form. It plays an important role in integral systems where you often, if you can reduce your equation to that kind of equation, it's useful because basically you flow by an inner automorphism. So you stay within an orbit and then you can find the integral of motions. But for us, the motivation is mainly this equation interpreted from gauge theory. So we have a gauge theoretic interpretation. Where if you start with the cylinder, and so you have two parameters, let's say t. I'll take the interval I to be the compact interval from 0 to 1. And then we have an angle theta in S1. And if you look at connections on the trivial principal bundle over the cylinder, so this takes the form of in coordinates as a G-value one form where A0 and A1 are maps on the cylinder to the Lie algebra, and the curvature, if
D
you
theta. It's a D theta.
I didn't get that, sorry, Marco.
It's D theta.
Sorry, I can't understand. Can you maybe
Expression
speak a bit further from your
A0 dt.
microphone?
It's A0 dt plus A1 d theta, maybe?
Oh, yes. Thank you. Yeah, I think if you speak too close to the microphone, there's a lot of distortion, so I can't really hear. But
Okay, sorry. I'll be more gentle. Yeah.
that's better. Thank you. Okay, so the curvature is so dt a1 minus d theta a0 plus a0 a1. And so if you look, so this looks a bit like the Lax equation. And if, in fact, if you look at connections which are S1 invariant, so S1 invariant connection on the cylinder, then let's say, S1 invariant flat connection, this is exactly the same as a solution to the Lax equation. And so this interpretation is useful because now you not only have an equation, but you have an equivalence relation. You have the group of gauge transformations which act on this. So if you look at S1 invariant gauge transformation, so this is simply the group of maps from the interval to G, and we'll take them C2. Then this acts on the space L of solutions, let's say C1 solutions to the Lax equation. And so you can think about the moduli space of solution to the Lax equations, although this group is a bit too big, so the moduli space is trivial, but if you take the restricted gauge group, the set of maps where G is trivial at the boundary points, then this acts on the moduli space, on the space of Lax equations, and you construct the moduli space I, which is now a finite dimensional smooth manifold. So this is the basic moduli space of solution to Lax equations. So this is finite dimensional smooth symplectic manifold. And basically the symplectic structure comes from Hamiltonian reduction, because you can view the curvature equation, the Lax equation, which is the curvature equation, is a moment map for the action of the gauge group. And so this, by Marsden-Weinstein reduction, you get a symplectic structure. And not only it's a finite dimensional smooth manifold, but you can actually identify it explicitly. So if you think of, well, there's a canonical isomorphism with the cotangent bundle of the group, which you can think of as G cross the Lie algebra, where basically if you have a connection A, well, you can split it in two parts. So you have the A0, and you can think of the A0 dt as a connection on the principal bundle over the interval, and A1 as some kind of extra field. And by thinking of it like that, the Lax equation becomes that this field is covariantly constant with respect to this connection. And so this means that, well, first of all, the connection on a path is completely determined by its holonomy. And so you get an element of the group by taking the holonomy of this connection. And then since the Lax equation is that this A1 field is covariantly constant, it's determined by any value at any point. And so, for example, you can take the initial point, and that gives you a well-defined smooth map from this space to that one. And it turns out to be an isomorphism, a diffeomorphism, and even a symplectomorphism. And even more than that, we have, so we have G, the full gauge group modulo the restricted one, which is isomorphic to G cross G. So this is this still acts on there's a residual action of this on the moduli space. And then this action is actually Hamiltonian with moment map, which takes A and takes the boundary values of the A1 field. So A1 of 0, A1 of 1, and there's a minus sign here. So it's a Hamiltonian G cross G manifold just like the cotangent bundle is also a Hamiltonian G cross G manifold, and this is an isomorphism as Hamiltonian G cross G manifold. So here on this right-hand side, this is simply the G cross G action lifted from the action by left and right translations on left and right multiplication on the group G. Okay, so this is all classical, well-known facts. And this is the starting point of this work where, so the idea is that we started with a cylinder, okay? And by thinking of it as kind of a contracted version, the interval, we went from flat connections on the cylinder to some kind of moduli space, MJI, which is smooth and symplectic. And so one question is, if you start with a general surface, is there a way to do something? This is very heuristic, but is there some kind of generalization of this construction where you get some moduli space from this surface by taking some kind of S1 invariant, but there's no S1 action really on this surface. So how do you do that? Well, the idea is that you kind of contract the surface. Imagine you just plug all the boundary components and then you just suck out all the air inside the surface. What do you get? So this slowly contracts inside some kind of thin tubes, and maybe, I mean, it's not canonical, but you can contract it in some way until, if you do this in the limit, you end up with a graph. Okay, so of course there are many graphs, many ways to contract it into a graph, but this is the idea. And so once you have this graph, you want to assign a moduli space to it, which is some kind of deformation of the moduli space of flat connections. So it's clear what will happen on the edges here. On the edges, we'll have the Lax equation, but it's not clear exactly what do we have on the vertices. How do we attach these kind of deformed connections on the vertices? Well, what is clear is what the gauge group will be, because the gauge group is just a group of maps. In the basic case, is the group of maps on the interval to the group. And for flat connections, it's also the group of maps on the whole surface to the group, trivial at two boundary points. And so the gauge group will be just the map, the space of maps on the topological realization of the graph with trivial boundary points. And then we can infer what happens at the interior vertices by requiring that this action is Hamiltonian and just looking at the moment map. So the moment map equation will give us the Lax equations on the edges and a kind of Kirchhoff law at the interior vertices, meaning that the A1 field will have sum of incoming values equal to sum of outgoing values. So once we have this idea, we construct, the goal of the paper is we construct this moduli space starting from any quiver, as long as it has non-empty boundary, at least one of these points exist. So we construct this moduli space, show it's a smooth finite dimensional symplectic manifold. And then we show that if we kind of inflate back the quiver to a surface, this symplectic manifold does not depend up to symplectomorphisms, depends only on the topology of the surface obtained from this. And then we explain how to glue these surfaces together to get some kind of TQFT and how to deform from the moduli space of connections to that. Okay, so let me define this moduli space now a bit more precisely. So first of all, what do I mean by a quiver? So a quiver, for those that don't recall, is a tuple, we call it gamma, of a set of vertices, edges, and two maps S and T. Where S and T are just maps from, oops, the other way around, edges to vertices. And V and E are just sets, just abstract sets. So in other words, a quiver is just an oriented graph with possibly multiple edges and loops. So that's an example of a quiver. And on a quiver, we have what we call the boundary of the quiver, which is the set of vertices of degree 1. Okay, so those are the vertices where there's just one edge attached to it. So this is a boundary. This is a boundary. We assume the quiver has no isolated vertex, just to avoid trivialities. So this is the boundary, and the boundary decomposes because we have orientation on the edges into two disjoint sets. Those where you have an incoming edge and those with an outgoing edge. So in other words, the gamma minus are those that are the source of an edge, and those are the ones that are the target of an edge. And the other vertices, we call them the interior vertices. So all the vertices that are not on the boundary. So these are the interior vertices. Okay, so starting with that, we attach a moduli space to this. So first of all, we take a copy of the compact interval from 0 to 1 for each edge, and then we can form a big one-dimensional manifold by taking the disjoint union of all these edges. And then there's a topological realization of this, this quiver, which is just I modulo the obvious equivalence relation, which attaches these intervals at the vertices. Okay, so the moduli space, we start with a big Banach space B of maps from I to G cross G. So it's just a bunch of pairs of maps on each edge, and we take them to be C1, just so that the Lax equation is defined and continuous. And then we have the gauge groups. So as I said, the gauge group is easy to generalize. It will just be the maps on the topological realization of the graph to G, such that there are C2 on each edge. Okay. And there's a restricted gauge group, which are maps that are trivial on the boundary. Okay, so this big space B here is a Banach symplectic manifold, where the symplectic structure is just integration of the symplectic structure you have on G cross G by taking an ad invariant inner product. So you fix an inner product. Sorry, this is a bit small. You fix an inner product on the Lie algebra, an ad invariant inner product, and then this gives you a symplectic form on G cross G, and then by integration you get a symplectic form on the Banach manifold in the sense of infinite dimensional manifolds. Okay, so that's the setup, and then we can see that this Lie group G, this is a Banach Lie group, acts on B in a Hamiltonian way, where the moment map takes this form. So it has a moment map, usually maps to the dual of the Lie algebra. But here you can replace the dual of the Lie algebra with any other space that has a non-degenerate pairing with the Lie algebra. In this case, there's a non-degenerate pairing with continuous maps on from I to the Lie algebra. Sorry, continuous map from the Lie algebra. No, yes, that's it. Here I is the disjoint union of all the intervals on the edges, so it's like maps from 0, 1 to G to the number of edges, but you can just write it like that. Times as many copies of G as there are interior vertices. So you can construct a canonical pairing between these things. And then the moment map is simply the Lax equation in the first component. And then in the second component, this is where the Kirchhoff law happens, because it's so for all interior vertex V, you get a sum over all edges whose target is V. And then you take the A1 field at on the edge E, evaluated at 1, minus E in source minus 1 of E. And this is for V in the interior vertices. So in other words, if you have a vertex V and then you have many edges, some coming in, some coming out, and you look at the A1 field, I denote A1E to be A1 restricted to this interval IE. And then, so the values of this A1 field on an incoming edge, they all sum to the same as the values at this vertex of the outgoing edges. Okay, so then you can construct the moduli space. So the moduli space, which is mg gamma, so this is the moduli space of solutions to the Lax equation on the edges with the Kirchhoff law on the interior vertices. So now the fun part is, well, this is just a definition, but is to show rigorously that this is actually a finite dimensional smooth symplectic manifold. So we construct slices for the action and all the analytic considerations to make sure that everything in the infinite dimensional version of the Marsden-Weinstein reduction holds and so on. So the theorem is that if, so this is the bulk of the paper really, if gamma is connected and has non-empty boundary, then, so first of all, mg gamma is a smooth finite dimensional smooth symplectic manifold. Also, so everything that we had in the classical case of just an interval generalizes. So it's a finite dimensional smooth symplectic manifold, but also we had this Hamiltonian action for each point in the boundary of the interval. So the same happens here. If you look at G, the full gauge group, modulo those that are trivial at the boundaries. So this is isomorphic to G to the number of points in the boundary of the quiver. So this acts on the moduli space. There's a residual action in a Hamiltonian way. With the moment map, so this is a map from mg gamma to g to the number of boundary points, which also records the values of the A1 field at the boundary points. So this is A1, let's call it V for V in the boundary, and then there's a sign of V, where the sign of V is plus if it's in the an outgoing boundary, and minus if it's an incoming boundary. So this is a Hamiltonian space. And also the identification with the cotangent bundle generalizes this mg gamma. You can identify it once you know it's a finite dimensional smooth symplectic manifold. Then you can show that there's a symplectomorphism, in fact, an isomorphism of Hamiltonian spaces to cotangent bundle of G to the E modulo an action of G to the number of interior vertices. And so let me explain this action in a bit more detail. So let's say you have a quiver. I'll do it bigger. And you focus on just one edge. Let's say this edge here. So we attach a copy of, so we will focus on the vertex. So we attach a copy of the cotangent bundle on each edge. And then we have to define an action of G, G to the number of interior vertices. So basically, if you take an interior vertex like this one, then this is a Hamiltonian G cross G space. Okay, so it has a G cross G action on it. So in particular, if you take this this interior vertex, then since it's on the right of the edge, it induces an action. Let's call it G right, an action of G on this cotangent bundle. But also it's on the left of this edge, and so it has an action. There's an action of G left on this one, and also G right on this one. So do you have three actions? And if you just take the diagonal action, just one copy of G acting on this, this gives us the one of these G actions. So for each vertex, you have an action on this, an action on that, and then you take the Hamiltonian reduction by this diagonal action. So you do this at every interior vertex, and then you get this symplectic manifold, which is isomorphic to that one. All right, so once we have these moduli spaces, let's discuss how do they behave with some operations on the quivers. So first of all, let me recall a fact, basic useful fact, which will be useful for our discussion, is that for a Hamiltonian H cross G manifold, M, you can take M cross the cotangent bundle, which is now a Hamiltonian H cross G cross G cross G manifold. Okay, because T star G has two G actions, and this one has these two. And so if you take these two copies of G and consider the diagonal copy of G inside these one, you can take the Hamiltonian reduction by this G. So in other words, G acts on M in the original way from this G action, and on this one by the left translation. And so this one is now a Hamiltonian H cross G manifold, because these two actions persist to the quotient. And so starting from a Hamiltonian H cross G manifold, you get a new Hamiltonian H cross G manifold. So what is it? What is this new Hamiltonian H cross G manifold? Well, turns out it's not really new. This is not something you can use to make new Hamiltonian manifolds from all, because it's isomorphic as a Hamiltonian H cross G manifold to M itself. Okay, so it's, in other words, this cotangent bundle is some kind of identity for Hamiltonian spaces. Okay, and we'll discuss that in more detail in a categorical sense later in the talk. Okay, so that's a useful fact. If you take the cross product with D star G and reduce by this diagonal action, you get back the same manifold. Okay, so let's apply this to our moduli space. If we take mg of a quiver, and okay, so let me just take a random quiver. And we consider this edge here. And from the, let me just recall the previous result we had, that this cotangent, this moduli space can be identified with a symplectic reduction of a copy of T star G for every edge, modulo this action of the interior vertices. Okay, and so there's a T star G here, which is attached to the rest by a Hamiltonian reduction. Okay. And so if you apply this basic fact to this, then you realize that this moduli space you can identify with the moduli space of a graph, another quiver, where you delete this edge here and you bring these two together. Okay. Because this cotangent bundle is attached by Hamiltonian reduction, and so if you just do it for that vertex, you get just all the cotangent bundles here, which are not attached, just kept with their diagonal, with their G actions on each vertex. But then you do the reduction on this side, so this attaches these things into a vertex. And so by this basic fact, you can contract all the edges of your graph, as long as you have at least one edge on both sides. So the number of edges on both sides of this contracted edge has to be non-zero. Okay, so in other words, another way of formulating this is that mg gamma 1 is the same as mg gamma 2 if gamma 1 and gamma 2 are homotopic, where this homotopy is kind of a discrete version of homotopy for quivers, where gamma 1 and gamma 2 are homotopic if one can be obtained from the other by a sequence of moves of these forms, or a sequence of moves where you have a number of edges on one side, number of edges on the other side, and you identify this with the contracted edge, where the number of edges on both sides is positive. So, for example, you can start with, let's say that one. And then this will be homotopic to that one because I contracted this edge. But this move can be performed in either direction. It's just not contraction. It can be expansion also. And so, for example, you can, this would be the same as this one, where here I added an edge here by expanding here. So this quiver, I didn't put orientation, but any orientation work is homotopic to that one. Okay, so the moduli space just depends. It's like a homotopy invariant of the quiver. And using that, so first from a quiver, we can, as I said at the beginning of the talk, we can associate a surface by doing the opposite thing of contracting the surface. We now inflate it. So if you inflate the quiver, now this is well defined. There's a unique way, well-defined way to do this, where you get a surface by just replacing every edge by a cylinder and attaching these edges by punctured spheres at the vertices. So you get something something like that. So this is the surface you obtain by inflating this quiver. But it's not just a surface, it's an oriented surface with oriented boundaries, because these boundaries here have orientation. So this is minus, minus, plus. And so this also comes with orientations on the boundaries. So in other words, it's a cobordism. So from a quiver, you get a canonical cobordism. And then it's not too difficult to check, which we do in the paper, that gamma 1 and gamma 2 are homotopic in this definition, if and only if these cobordisms are isomorphic as cobordism, so preserving the boundaries. And so from that, we have a well-defined moduli space attached to any cobordism with at least one boundary component. So you defined mg of a cobordism to be, well, it's only defined up to symplectomorphism or isomorphism of Hamiltonian spaces. So I will put a bracket to denote an equivalence class, but you define this if sigma is the isomorphic to the cobordism associated with the quiver gamma. So another useful thing is that this cobordism, you can read off the genus and the number of boundary components by combinatorial data of the quiver, namely the genus G, can think of it as the genus of the quiver, is the number of edges minus vertices plus 1. And you can see that this is a homotopy invariant, because if you do this this move here, you remove an edge, but you also remove a vertex, and so the E minus V stays constant, and the plus 1 is just to match the genus. So it's a cobordism of genus E plus V minus plus 1, and from the number of circles is M gamma is the number of incoming boundary components, which is also a homotopy invariant to N gamma a number of outgoing boundary component circles. Okay, so now that we have these moduli spaces, so cobordisms are meant to be composed. If you look at the cobordism category, so what happens if you compose these cobordisms? So this is another theorem in the paper. Which, well, I'll just draw an example, but it's easy to infer what is the general statement from that. If you have a surface, let's do this one, which you chop into two parts, two surfaces, by some cycle here, then you can get the same moduli space, or at least an isomorphic one, by taking the two moduli spaces associated with each piece, attach in some way. What and how do you attach them? Well, here, this boundary component has an associated G action on the moduli space because there's a G action for each boundary component. And there's another one on the other side by this boundary component. And then you can do the Hamiltonian reduction by the diagonal G action. And this is an identification. So this moduli space is isomorphic to this symplectic reduction of the moduli spaces. And this has, so this look a bit like a functorial relationship because this is composition in the cobordism category. And indeed, you can also interpret that composition in a functorial way. Which is similar to ideas of Moore and Tachikawa, which were the first to consider these kinds of TQFTs, where the domain of the functor will be the cobordism category, but the codomain will be a Hamiltonian category where objects are now compact Lie groups. And morphisms, so a morphism from G to H will be, so we want that these are morphisms and this is composition. So how do we do that? Well, the objects are the Lie groups and the morphisms are the Hamiltonian G cross H manifold. And then you do composition by Hamiltonian reduction. So if you have, let's say, M and N, then M composed with N is their cross product reduced by their common H action. So here H acts on M, N on N, and so you can do the Hamiltonian reduction. And the identity is precisely the cotangent bundle as a morphism from G to G because it has a G cross G action. And so this is the true sense in which the cotangent bundle is the identity. So technically, this is only a partial category because these H actions here are not necessarily free. So this might be singular, but you can always complete it into a category by taking, you first start with composable morphisms where this action is actually free. And then you complete it to a category by replacing morphisms by sequences of composable morphisms. No, just sequences of morphisms, not necessarily composable, up to the equivalence relation that if you have adjacent pairs that can be composed, then the composition will be equivalent. So this is like just a formal trick to complete a partial category to an actual category. This was first used for the Weinstein-Lagrangian category, the symplectic category where the morphisms are Lagrangian relations, they cannot always be composed, but you can complete it to a category by this trick. This was sometime the first to do this were M and Woodward. So sometimes called a Woodward trick. To complete. Okay, so in any case, we have a category, and here this is composition in this target category, and so you can package this into a theorem which says that there exists a unique symmetric monoidal functor MG, which goes from cobordisms, two-dimensional cobordisms to this category, such that the circle is mapped to G, and the cobordism associated with a quiver is mapped to the moduli space of Lax-Kirchhoff equation. And finally, to conclude, I want to go back to the original motivation of flat connections. So you can wonder if you can make this a bit more precise, this heuristic. So let me go back to the beginning. The heuristic was to take moduli space of flat connections and contract the surface to a quiver and then get a moduli space. So more precisely, once we have the moduli space, we can argue as follows. So if you have a general surface, let's take this one. Okay, so this is your surface. The idea is to chop it into pair of pens. So you do a pair of pens decomposition. So into cylinders and a pair of pens. And then once you have that, you just choose a point on each cycle that you produced. And then you join these cycles in any way. As long as you have only one edge on each boundary components here. Then the moduli space of flat connections is completely determined by the holonomy on these loops here, on the one you use to chop the surface, the ones on the boundaries, and the one on the edges. And then once you have that, then you can define in a rigorous way a smooth deformation to, so if you look M flat on that one, this has a smooth deformation to mg of this this quiver here you have inside. In the sense that you can construct a big space D here with a map from D to R, so a surjective submersion, such that the zero fiber is this degenerate moduli space, and the non-zero fibers are isomorphic to that one. So for all t non-zero, and furthermore, you can even construct a single two-form on D such that the pullback of this two-form to every non-zero fiber is the quasi-Hamiltonian two-form on that, and the pullback on the zero fiber is the symplectic form you got from this one. And so this brings back to the heuristic which we use to construct these moduli spaces. Okay, so I think that was 50 minutes, and it's exactly at the point where I wanted to stop. So thank you.
Okay, thank you so much. Oh, there are even floating hands. Interesting. Um, how is this family constructed? The D?
The D, it's using, well, as I said, so the holonomy determines the connection. And so you have, for each of these things, so here the cylinder will give us the double, so G cross G. And here you'll have dg squared, dg squared, dg squared. And basically you deform the double G cross G to G cross this by taking the usual deformation space of G at the identity, which is something which whose generic fiber is G and whose central fiber is the Lie algebra. And so using this, you can deform each double to a cotangent bundle, and this is the deformation basically.
So does this mean that you have a family in the family D? So there's a corresponding kind of degeneration of quasi-Hamiltonian spaces that goes to a Hamiltonian space in the central fiber.
Exactly, yes.
So that's true before you mod out. So there's something more fundamental than D, which is like the quasi-Hamiltonian spaces, and it's like a family of quasi-Hamiltonian spaces that degenerates to a Hamiltonian space, and then you can take the reduction of the whole thing.
Reduction, well, each fiber is, oh, you mean, what do you mean by reduction? What reduction?
I just mean that that here you have a family of moduli spaces. The
Yes,
generic fiber is a moduli space, which is a quasi-Hamiltonian quotient,
yes.
right? So can you construct the whole family as a big quotient of some family of
Oh.
quasi-Hamiltonian spaces?
You mean like construct D as a moduli space itself? Is that
Um,
what you mean?
um, I just mean so D is a family of moduli spaces, most of which are quasi-Hamiltonian reductions, but the central fiber is a Hamiltonian reduction. Is that
Yeah.
right?
Yes, that's right.
Okay, so can you express the whole family as a reduction of something, some kind of thing before that?
Um,
The reason that I'm asking is just because it's weird, like it's weird that a quasi-Hamiltonian reduction itself would degenerate to a Hamiltonian reduction.
well, we have another paper with my student Mohammed that is specifically about these kind of things. So we
Ah,
define what is a Hamiltonian deformation of a quasi-Hamiltonian manifold to a Hamiltonian manifold. And one of the construction results we have is that if you have a Hamiltonian reduction, you can deform it also to a quasi-Hamiltonian reduction, you can deform it to a Hamiltonian reduction.
ah, very interesting.
Yeah.
Any questions?
If your okay. In in your diagram, you have the surface decomposed into pairs of pants and cylinders.
Yes.
Why? What difference does it make to have cylinders? Since a cylinder, you can contract the cylinder into a circle, so
Yeah.
you can contract away all of the cylinders. What is lost if you? What is the difference?
I mean, no difference.
What
Just
is the difference of having the cylinders?
I,
What is being added?
I included the cylinders just that you have more graphs, more kind of quivers that you can obtain in the target of this deformation, but you can avoid cylinders if you like. It's just to have different. I mean, the deformation depends on the choice of graph you embed in. And so if you have this cylinder or not, it's kind of a different deformation because
Okay, they're different graphs.
yes, they're different graphs. So the moduli spaces and the deformations will all be isomorphic, but different. It's always canonical once you choose, just to allow more graphs, basically. Yes.
Okay, thanks.
When you so I understand that in the first part of your talk, you were speaking about the Lax equation in relation to flat connections, and then you finally kind of using the theorem, the first theorem, you expressed it all in terms of quasi-Hamiltonian reduction of products of T star G. So you were able to build these things out of T star G, right?
Yeah.
So at that point, does it no longer depend on G being compact? So do you have this functor for a complex group or a reductive group?
Right. If you just define it, where is it? If you just define this, this could be defined for a complex reductive group, and in fact, you can even obtain it as a moduli space of solutions to the Lax-Kirchhoff equation, if you like. You get something hyperkiller. We just didn't really wanted to do the analysis of that case, but this could be done. So this G here could be complex reductive, for example, and then you'll get something analogous. To show that this is a finite dimensional smooth symplectic manifold, we use compactness in the analysis. But if you want G to be complex reductive, as I said, you can replace Lax equations by Lam's equations and use the compact real form and still get a moduli space.
Okay, but for the purpose of obtaining a TQFT for every group G, what if you kind of ignore the analysis component and you just go to the Hamiltonian reduction arguments, what kind of groups fit into this? For which groups do we have this TQFT?
I guess it should be pretty general. I mean, you need this to be smooth. So the action, I'm not sure if the action will be free. I'm not sure if it will be proper for any group. But as long as these actions are proper, you'll get the TQFT, yes. Or even if you are willing to get into singular spaces, it will be formally a TQFT. Like, for example,
Right,
if this
right.
is an algebraic group, and then you're willing to replace varieties by just affine schemes, this will give you a TQFT.
Okay, thank you. Any other questions? Is anyone online?
I have a question. Can you recover the groupoid structure on T star G in terms of this, well, in like this moduli space or this picture? Do you know how to?
Yes. So the groupoid structure is just concatenation of
It's just that.
intervals. If you go back to the original one, where is it? So you look at moduli space of solutions to Lax equations on an interval, and if you have two solutions, and then you do the concatenation, the source and target maps will be exactly these moment maps equations,
Right.
which records the boundary value of the field.
Yeah.
And so if you have A1 matching with the A1 of the other ones, then you can concatenate them and then do well, you have to adjust a bit so that the A0 fit as well, but this can be done. Yeah.
Okay.
So for a graph, you get something marginal, like a monoidal groupoid. So it's something, I mean, it's not a groupoid, but you can concatenate these graphs together, but there will not be an inverse necessarily. So that's like a mono. We discussed this with my student. We're wondering if there's this notion of a groupoid, but a monoid. So it will be a monoidoid. I don't know if that's a thing, but
Me neither.
Someone working on it. Thomas has been working on monoids,
sorry,
but he calls them
Oh, really?
categories, holomorphic categories.
Okay. I understood holomorphic categories, but I didn't understand the part before.
Oh, sorry. There's a member of the group here, Thomas Stanley, who is working on such monoidoids,
Okay.
but they're called holomorphic categories.
Okay, interesting. Is there a
Just
paper on
because,
that?
well, he's writing up his thesis. It should be done within a couple months, and maybe you might be interested in being the external examiner.
Okay.
I have another question. So, this might be related to what you said about the norm equation.
Mhm.
So, do you see a version of this in which the length of edges becomes important? That the graph should be endowed with a length?
Yes, if you want to think of them as Kähler manifolds, so you want to retain the metric, these moduli spaces are Kähler manifolds. And the Kähler metric, if you glue intervals, it will be scaled. I mean, it depends on the length, the total length of the intervals. I haven't really tried to prove this in detail, but my guess is that the Kähler metric on the graph. So this, just for intervals, this is definitely true. If you do it for a graph, I guess the only invariant will be the total length of all the intervals, but I'm not 100% sure. This is something we should check.
My second question was going to be whether whether there are angles between the edges in that case, so that you have a form of the conformal structure.
The angles are not really used. These are just abstract quivers obtained by like set theoretically. So we don't really think of them as embedded in R2 or anything in any way. So I don't think the angles will play a role.
Right. The reason I ask is because if you're seeing that the moduli space of flat connections is the central fiber, right, then that thing is supposed to be Kähler, and the Kähler structure is supposed to know about the conformal structure on the Riemann surface. And so if you're representing the Riemann surface by a graph, then presumably you need to incorporate the conformal structure in that graph somehow. And I thought maybe lengths of edges and maybe some kind of angles, but I'm not sure.
That's interesting. Yeah, I'll think about that. Good point.
You could even have like momentum conservation at each vertex, right? Because in the same way that you have momentum conservation for the elements of the Lie algebra at each vertex, you could have some kind of other some kind of planar angles or vectors, some kind of, yeah, I'm not quite sure.
Yeah, I see what you mean. The sum of the vectors will match, of the incoming vectors will match the sum of the outgoing vectors.
Yeah.
Yeah.
Okay, well, thanks very much for explaining your paper. It was very clear. And if there are any last questions, if not, let's thank Maxence.
Thank you.